So my main talk today is about control design, and I try to explore how we can embrace or reject a wind source. So it's my pleasure to be here, and I will try to explain the current work. So this is the content or outline of my presentation. As you can see, we wanted to explain more about wind and wind energy. So you have already discussed about this and my research background. But what I wanted to say is I tried to explain my previous work, what we have done before. This is just a small presentation or outline, which should be based on the physical systems that we have used. So one of the systems which was during my PhD work is about the power line inspection robot. As you can see, ideally now people use manual inspection. So from here, we can see we have some people or a lineman who will climb the line and inspect the line. So inspecting the line, performing an inspection, then the subsequent inspection and maintenance will be tedious, and this will require a lot of time and is highly dangerous. So what we propose is to use an alternative method, which we have a robot to do this work for us. So this is my setup that I built, and it was a simple setup, but the main thing is we want to see how we can inspect this line without the use of human. So in that, we can have improved safety, we can have more efficiency of the supply, especially we don't need to cut the power, no outages of the power. And also, unlike the human who will be tired, the robot will work for quite distant, especially we know all these power cables run for hundreds of or even thousands of kilometers. So it's very important to have a robot who can, which can replace the human operator. So this research can have many aspects. Of course, the vision is there, image recognition, many things. But for our own part is the motion control, how we can see our robot moves along the line perfectly. However, to have this, we have issues with wind because these power lines, they are highly above the ground and they can have effect of wind. So this part of the research, we try to avoid the wind. We want to do something which will reject the wind, unlike in other places that we will embrace it, which we can use the wind. So in here, we try to simulate the wind using industrial fan. And also we have setup or the laboratory setup for the tower. We assume this is like the real tower, and we have the real power cable. And now this system will move along the line, and we try to control the motion of this and also the oscillations that will follow when the system is moving. Then we have another system. This is an elderly assistant robot. With this robot, we know elders, the population is aging. So if the population is aging, we need the burden on the economy and the burden on the government, like for nurses, for the doctors. So there is need to provide an alternative, something that will help the elders. So we have developed this robot, which is the elderly assistant walking and sitting assistance for the elders. So we can see we have two modes. One here is the walking assistant. So we can make the robot to walk, so it can help the elder in walking. And we have, this is the sitting. So the elder can sit and can move around. So the same thing here, we have many research objectives, but what I did here is about the vibrations control. We can see here we have different types of the roads. In reality, there are different types of the roads. We can have asphalt is there, interlock is there, and potholes sometimes. So we try to see how the vibration affects the human, especially in the ride comfort for the elder. So to have this, we need to analyze the vibrations that was induced from the tires or from the road. And we have to check if it is based on the ISO. We have ISO, the comfort zone. So when will it be bad for the human, especially for the elders, and which range we have the optimal operating range, which range is accepted by the World Health Organization and others. So this is the main research about this. So then also there is this research about the flexible manipulators. These flexible manipulators, we can use them, or they have been research of recent, especially in the medical field, where you want to use the needle, the flexible needle for operations and sometimes for diagnostics. So we need this needle to be flexible. If it is rigid, it can be dangerous. So, but if it is this flexible, then it might have a vibration at the end, which is the tip deflection. So we try to control this tip deflection, which is the beta here. Then there is a basic control, which is about this inverted pendulum. The application of inverted pendulum can be seen in the rocket launchers. You can see the rocket normally at the end point is detached. So this detached need to be exactly balanced. So this balancing of this inverted pendulum is a well researched topic, which is based on the deflection angle. So we want to maintain, always we want to maintain the angle of this inverted position at 0. So this is the stabilization problem. Then now we will explain about our main current research. This was the previous research. So now for the current research, and we will try to explain some of the preliminary results. So if we look at here, we can see this wind can be accepted or rejected in this form. For the embracing, we are happy for the wind because we will harness this wind to get energy. So in the form of wind turbines and wind power generations, this wind is welcome. We need it. But in a place like this, where our systems like the cranes and the flexible manipulators in the outdoor, we don't want this wind because it will have a devastating effect. So now here we want to reject it. So now we have two topics to discuss. So if we see here, now we try to say, now let's see the state of the art. We want to explain what we do before we can come to our main research. The main thing is we need the modeling in most cases because sometimes you have to do the simulation first before you do the experiment. So how can you perform a simulations analysis without the model? So now we need to derive the modeling. So in this modeling, normally we have Newtonian equations or Lagrangian equation, which are the physical laws. We change our system into schematics, and from there we derive the equations. And after deriving the equations, we now we apply our control. And this control algorithm can be different types. And from there, we try to analyze. Now we try to analyze how this system behave and what need to be improved, or if the system is good or bad. So based on the analysis. So this control, which is the main research, can be divided into two parts. We have the open loop control or feed forward control, and also we have the feedback control. So, and sometimes we use a hybrid control. With this hybrid, it means we take the advantages of the open loop and the closed loop controllers, and we get a hybrid control. In this form, we try to have minimal sensors, because in the open loop or feed forward, normally we don't need sensors, the feedback sensors. So if in another system which requires a lot of feedback, if we have hybrid, so it means we have minimized the number of feedback sensors or computations. So there are many types of this feedback and feed-forward controllers. As we can see, the most prominent one is the PID, but there are more advanced ones. And for the feed-forward, we have input shapers, which can be positive, negative, or output based. So we take the case study for this wind combustion system as one of the cases where we need the wind. Of course, not to the extreme, but the wind is utilized here. So basically, this wind, there is a turbine blade which will rotate the wind will rotate these turbine blades. And these turbine blades will have a generator which will capture these rotations, and at the end it will be converted into electricity. So the background for this wind energy we can see is that the wind farms has been increasing, and we have a lot of improvement. We can see there are a lot of things regards to how the trend is. So from 2010 down to 2018, we can see there's an exponential increase in the adoption of wind energy. So how do we adopt this wind energy? Of course, we need sophisticated setup which will improve the efficiency and also will help for the safety of these blades, especially these blades. They are highly above ground. So if there are issues when they were running at high speed, if they can fall down, it can be disastrous. So wind exactly is a renewable source of energy. It's clean, and the wind almost is everywhere. So it can be easily harnessed, and it is environmentally friendly. So in here, we can see this is the process, how we can generate this wind energy. We have the mechanical coupling. There is aerodynamic things from the wind. And then we have the generators. Then the generators will be getting the mechanical energy. Then it will be converted to electrical energy. And it will be supplied to the grid or consumers. So from here, we can see from this dynamics, this is the wind that can be generated or harnessed, the power of the wind. So we can see it depends on many parameters, and most of them, they are proportional, meaning the area of the blades is there, how big the impact of the wind is on the blades, and the density of the air, also the speed of this wind. So how this spin, the wind speed, how the wind is coming or is attacking the blades. So we now explain about the problems. What is the problem associated with this wind? We can see, especially with this our setup, this wind is varying. The nature of the wind is changing. So how do we have our own control to cope up with this varying nature of the wind? So we need highly advanced wind measurement setups. But normally there are traditional anemometers, and also there are predictive algorithms that we are used to predict the wind. But all those things might be only for a short-term prediction, or they may need a lot of computation. So there is a method which is based on sensorless wind estimation. So we want to come up with a method that we can estimate this wind profile without measuring it directly. Because we know whenever there is this wind acting on the blades, so the aerodynamic torque will be generated. So from this aerodynamic torque, we can estimate using the relations to estimate the wind speed. So here, this is the dynamics of the equation. And from here, we can see this is the aerodynamic torque, which will be captured from the wind on the blades. So in many researches, they try to assume the nature of this torque to be slowly varying or slowly changing. But so in some cases, which is a practical case, it might not be the case. Sometimes this wind can be changing fast. So how do we cope up with that? So there are some estimators or observers that we use. There are many types. We have different type of estimators. So in our case, we want to estimate this torque, and we try to assume this torque has up to second order. So it has second order. So we try to estimate this wind, and based on that, we have our control law, and based on that control signal, we want to control the system. So normally we can generate the synthetic wind using some equations, of course, and also we can get the data from the wind farms from online sources. So this is one of the equations that we have adopted for the wind profile, which we can see. This is the graphical representation of it. So we can see how the wind changes. The behavior of the wind is changing with time. So this is what we want. We want to capture our power based on the changing behavior of the wind. So this is the block of our system. We have the output of the generators. So from the outputs, we try to make this observer only using two terms, and we can have a lot of observed signals here. So these signals were used for the control design, and later will be feedbacked, and we can see our response. So these are some of the preliminary results associated with the estimation. So now we can see the estimation looks pretty well. We can estimate this torque disturbance using these estimators. We have zero order, exponential disturbance observer, and higher order. So we can see how we can make this observation pretty well. And we can see the error of the estimation error, and we can see the higher order, how we can estimate first order and second order of this torque. So what is interesting here is that if we said this wind is the higher order is zero, as in other research, we can see it is actually not zero, because it can be a high value. So it's not zero, so it might have an effect. So we try to analyze what this effect has on the power generation and on the speed of the generation, or the speed of the shaft. So now we try to do three cases. We consider three cases. So the first case is, we said we have used all the three observers. So meaning we have observed the zero order, the first order, and the second order estimations. Now these are three observers, and we incorporate them into the controller, and then we remove one of those observers, which is the zero order, and we only consider the first order and the second order. Then we only consider a case where we only use the zero order estimator. So now these three cases will give us information and insights on what is the influence of those observers, or of those varying nature of the torque or of the wind, to our control and to the generation of the power. So if we look at this figure here, we can see if we change this, the speed and the frequency and the amplitude of this wind, we want to see what happened when we change this, because the wind is not constant. So sometimes the speed is high, sometimes the frequency is high, sometimes the amplitude is high. So these three parameters we try to see. So in this case, we can see, of course, in any case from here, we can assume they were good. But when we try to zoom further, if we want to see what happened with this error, so we can see when we use the zero order, which is the third case here, the zero order, we can see the error is higher actually. But when we use the first order and the second order estimation, they almost give the same behavior. So they have a smaller error, which is good, but they are almost the same with the second order and the first order. Now the same thing with the power generation. We can see for the power generation is the same case. This is for the second order and the first order estimation. They are almost the same. but was for the zero order, it has a bit less power generation. So in here, we can see if we assume, of course, this is noisy because we make the speed 3 times. We increase the speed of the wind at highly varying. So in any case, we can see the response or the behavior remains. The higher order estimations, they are the same from first order to second order, but the zero order is a bit less. So this is very important because instead of having to use many estimators, now it shows us that there are ranges that we can only use the zero order, which is, it will work perfect. It will give us the needed response. But there are other cases that we need only the first order. So it means, based on our analysis here, the higher order, the second order, is not important because it adds nothing, almost nothing. They are the same with the first order. So we can neglect using the much higher estimation. We can only use the zero order and the first order estimations. So this is a summary of this. We can see if we look at the error, this is using the mean absolute error. We can see B 3 times and 1/3. We can see how the behavior looks like. So in any case, the zero order has more error. But when it comes down to a minimal speed or amplitude, here and minimal speed, we can see they almost converged. And the same with the power generation here. The power generation seems to be almost the same for 2 cases, which are the normal speed. And for extreme cases, we can see the higher order gives more power. But in most of the current research, actually, they don't use this much higher power. So based on this, it will see it is around maybe down here. So in this case, it means the higher order estimation is not even needed. So this is the summary of this discussion based on the wind energy combustion system. We can see that it is satisfactorily used to get our required objective if we have relative wind speed, because this is known. Almost all the countries, they know where the range of their wind. So we know the range of the wind that we have. So based on this range, we can actually use our estimators. So we know the estimators that we can be implemented. So the second part of the presentations is about rejecting wind. Now we have just finished explaining the wind was welcomed and we can even use it to generate power. But in this case, we don't want this wind. So also we have many systems, as I have said. We have these flexible manipulators, we have these crane systems and others. But now with this crane, which is also widely used now, especially with the increasing use or production in the industries, mining, construction sites, especially this figure as it shows, this is a construction site. We have high rises building, and with this high building, we need cranes. So how we use these cranes, they will be operating along rotational axis and also up and down the masses. So this is the setup that we used in the laboratory. This is a replica of this, but a laboratory setup. It has the same thing, everything. The weight is there, we can increase the weight, and the angle, the cables, everything, and the rotation. So the background of this is, these are many types of those cranes. You can see we have different types of the crane, and almost they have a similar objective. The main objective is to carry goods from one point to another. And these goods, we want to carry them without causing any oscillations. So what happens if there are oscillations or if the wind is high? So it will be disastrous. It can cause loss of lives and properties. And in this last figure, this happened in 2016 or 15 in Saudi Arabia. I think almost 1,000 people died. There was a high wind, and during that time there were some pilgrimage on a religious trip, and this were crane falls down and many people died. So it means it is extremely important to study the behavior of those cranes, and if there is any control method to use so that we can reject this wind, so or counter or compensation. So the main thing is the problems. If this way swinging persists, the load will be difficult to position. It will take time for the operators to move one goods from one point to another, and also it will reduce the efficiency. So there are many methods that we can be used to control. So there are open loop control, feed forward control, and feedback, as I discussed earlier. But the main thing is now these uncertainties and the wind disturbance, we need to take care of them. So this system was normally represented using, this is, if we assume this is the real system, in the real physical system, so we need to make it like the laboratory one. And from there, we can have the equations, which will be the physical laws based on the schematics, and we can generate our equations. So we analyze these equations, put them in the simulations, then make them in the laboratory scale, then finally implement them on the physical system. So we try to see what are the challenges or the trend, how this anti-swing control has been going on, and also what are the variables that we need to control and the limitations and the anti-swing thing. So one of these prominent controller is called the input shaping control. So this input shaping, what it does is you have the system which will be oscillating. So if there is oscillation, now you give a signal, you delay it in a specific time, it is delayed, and now at the end, now look at, this is the original signal, now this is the original response, the red one here. But if we try to make a delay, now we have a response, this, and when we delay it in a good time, now this will be cancelled out, and at the end we'll have a smooth response. So this is the basic idea of this input shaping. So we try to delay a signal, part of the signal, and later we will make a convolution of it, and we can obtain a good response. Of course, this one is in sometimes microseconds, you will not feel it, but it will give the response. So the basic idea is we assume the general behavior of the system is a second order. The response is second order, and we can get the time this is in time domain, and from there we assume the vibrations, the resultant or residual vibrations to be zero, and from there we can generate these terms that we use for the control. Now the blue one here is the control signal using the input shapers. So the black one, this is my contribution, which is part of my PhD. I tried to eliminate these oscillations, not oscillations, but chattering-like phenomenon. At this point, this is for representation only. We can see the time was almost 2 seconds, but in reality it is not. It's milliseconds or micro, but because of this staircase-like structure of the control signal, which is given to the system, so we have chattering. Actually, I was planning to add a video, but it was not in this computer. But when the system is moving, it will be making a movement like this, which is like a chattering one. So this is bad for the actuator, and also it can cause some additional oscillations. So what we do is we try to minimize this chattering. So the black one shows how we have improved this chattering or the delay. So we can see it is a more or less a smooth control signal. It will be smooth, and the response will be better, or has been better. So there are also changes, because as we said, this system, we can have variables like the mass. Now, if you are operating this crane, the mass will change. So mass is one of the parameters that we have to take care of. Then the length of the cable, because this mass can be taken from one point to another and can be moving up and down. So now this cable, which was initially assumed as constant length, so the length will vary. So when we change this lens, we can see how the behavior of these systems look like. So if the lens changes, the performance try to be adversely affected. So we try to check care of it. So what we did was we introduced this hybrid control. I tried to use a combination of the input shaping and another one, which is a feedback controller. So with this feedback controller, we try to add this feedback controller, which there are two types. I use the sliding mode controller and the fuzzy. In each case, we try to add them together and see what will happen in terms of the response. So these are some of the results. We can see here, when we use this, the fuzzy logic alone, the response was faster, but when we added this improved input shaping, the response was a bit slower, but still in time almost the same. But for the oscillation part, we can see how we have improved the oscillations. So we have reduced the oscillations of this deflection. And also we try to see a normalized behavior of this system, how changing those parameters affect the system in terms of velocity, settling time, and the root mean square. So this is actually what we did. So I just give a summary at the end, what we are currently doing in our research group. So the first thing is based on the wind energy combustion system. Here, we still use to estimate the wind, and we can control the generator speed, and we need to do estimation of the disturbance. And the current work is more concerned about the integration, how we integrate this, our system, with the grid or with other renewable energy sources like solar. So also there is this research which is based on active damper for earthquake. And we know there are some countries that are prone to earthquake. And this is a model of this system. This is like a building. So in this building, we have, this is like a 2-floor or 2-story building apartment. And at the end here, this is where we can simulate or generate the tremor, which is the earthquake. So if there is earthquake, of course, this building will be shaken. So after some time, the building will collapse. So this one is a good research point. And also we can estimate this disturbance here, which is the earthquake, and we can provide a counter or compensation time here. So this one has been implemented in many buildings, especially in China and in Taiwan, called Taipei 101. So this is one of the practical applications of this tuned mass system. Also, we have this, which is the motor control and disturbance estimation. Here we can try to see how we can estimate the disturbances and how we can reject them. And there is a control based on active suspension system for the car. This one is both on vibration control and also based on the ride comfort, analysis of the ride comfort for the human while we are moving in the car. So thank you.
Thank you for respecting the timings. It's exactly around 35 minutes for the presentation.
Yes.
It's very interesting. I learned a lot. It's not my field, you know. I'm in the power electronics, but it's very limited in microwatt or nanowatt. It's not in the range of in your research. Very interesting for this. So in summary, you have to correct me if I give the wrong idea. So the first one you mentioned on the model of your research, on that you provide how to calculate the torque, and you can estimate the wind speed, right?
Yes.
Yes. And then in the second application, you can reduce when you know the wind speed from that may create some vibration. So the point I told is not clear for me in the second presentation. It means you will provide the cancellation for the mechanical vibration, or the control system will provide the damping signal from the electrical power to reduce this kind of vibration, or I mean the oscillation of the mechanical system, right? Yeah. So
Yes.
I wonder what the application of your model to reduce the oscillation of the system in terms of mechanical or electrical. Yeah.
Yes, well, I try to explain almost 4 systems. And
Yes.
what I said is, if you look at it, we have, in this case, I don't know specifically which one you are talking about. And for system like this, we make a counterbalance. So now we have a vibration here, which will be, the vibration will be induced from this point. This one will be
Yes.
vibrating. So now we have
Right.
a counterbalance here. This is a counterbalance. So now we make a control signal so that this, if this one is vibrating, this one will provide a tuned mass, which will be countering along this line. So this mass will be constantly moving along here to counter the induced vibrations from here. So this,
I got your point.
yes, yes. So this is for this case. But for the other case, which were talking about for the crane, for this crane, we try to control the signal. Now, based on what we have, based on the impact of this vibration on our mass, so we have to control the control signal.
I see. So you mean here, firstly, your model, you can detect the vibration is from the
Yes.
mechanical, in terms, for example, from the earthquake, right?
Yes.
And then that can reduce somehow the degree of the imbalancing, and then
Yes.
you will compensate that by
Yes.
Providing with somehow another torque, right? To
Yes. Counter.
balance on the left or on the right in
Right.
terms of
Yes.
force.
Yes.
Yeah,
Yes.
that's great. Yeah.
Yes.
Yeah, it's somehow, I guess, your research we can apply in the balance for the drone. It somehow is similar, right?
For what? Sorry?
For the drone, the UAV.
Yes. It's the same thing.
Right?
It's the same thing. It's the same
Yeah.
thing. Yes.
Yes,
We have
because
to, even for the drone, we have to estimate the wind, which is the disturbance. So from there, you balance the disturbance.
the motor, right? But the point is, so that's why you mentioned in some slide about the response time is important, but somehow for the steel devices like the wing or the device is in the standby mode, it's different for the UAV, because the UAV, the time response is very crucial, because it can turn over the UAV. It can be
Yes.
fallen
No.
down,
It's
right?
the same.
But
This is just
now
it's
I
based on,
understand.
based on the response of the controller. So I said in some applications it is not fast. Sometimes it's slow response, so you can work with that. But in other applications which is highly fast, so your control has to be also fast. So it will counter and provide a counterbalance quickly.
I see. So maybe I'm sorry, I have to leave I'm sorry, the audience. I'm so curious. And may
Yeah,
I
it's
have one
interesting.
last question?
Okay.
Yeah. So my last question is more about, somehow this is your model, right? How can you confirm your model in terms of empirical testing, or some kind of on the hardware devices to look at the efficiencies of the algorithm, how much the resources you have to use, and response time, and the mechanical, the electrical power you have to provide to the system, for example. Yeah.
Yes. Well, you have asked many interesting questions. Initially, as I have said, in this modeling, normally when we make the model, there are some assumptions that were made. So these
Right.
assumptions, we have the parameters. Always there are parameters that define the system. So normally there is flexibility is there, the mass is there, which is the weight of the system, and also there are terms that we call uncertainties. So this uncertainty,
that's the more difficult to
yes,
control.
this is the part. So these uncertainties, this is for you. You have to define what are these uncertainties. We give them, you can say they are lumped. You just give a term, T or tau, and we can estimate actually. We can estimate those uncertainties. We can estimate them using, there are many disturbance estimators. So we can estimate these uncertainties, and based on that, our control algorithm will take care of those uncertainties. Yes.
So in your model, you count already some part of the uncertainty.
Yes.
Under some kind of parameter, right? Some
yes,
coefficient.
exactly.
I guess so.
Yes.
Very interesting. Yes. So now it's time for the audience. Sorry. So please, is there any, let me look at the chat. So we have some audience here. Is there anyone who, you may ask in Vietnamese and I have you to translate in English. Yeah, so as you know, in VPAC, we are a community. We work from the scale of nanowatt to megawatt. So yeah, we are in a wide range of power electronics, and it's very interesting to have the chance to work with, to update on some very interesting renewable energy from wind, right? So if you have a chance to go to Vietnam, we have a many green wind field, very nice, and usually they are around the shore where you can have a beach and you can swim very next to the wind field. It's very nice. And
yes. Actually, based on I checked the data, I see Vietnam gave one. They are given real-time data of the wind farms. I have seen it from the online resources. There are some data from Vietnam, yes, and it is verified, yes. So I believe you have these wind farms there. I hope one time Prof. Tong will invite me to Vietnam.
You know that in July there's the big conference in Vietnam, and Tong he's one of the track chair of the special session on the power electronics in July in Da Nang.
This July.
I don't know if you are aware of that.
No, I was aware of last year. There was one, I think December or something, but I don't know about this.
Oh, but this one is in the IEEE conference, and it's very big. Oh, you should know about that. You still have 2 weeks to apply for that because it's in the special session. So they extend the submission, and I guess you may try the conference in Vietnam. It's interesting. I would like to invite you. I'm the secretary of this conference. So if you would like to have more information, let me know. Right.
All right. Thank you.
Very interesting. Ahmad, I can call you Ahmad, right?
Yes, it's better. This is my name.
Yeah. So I guess our audience, they are shy. They don't have more question. But if you have any question, as you can see on the slide, and even we provide the email of Dr. Ahmad on the VPAC, you can send him an email at ahmad.harsan@nu.edu.kz, right? Oh yeah, there one question in the chat. The audience, they would like to ask you how to measure the motor parameter. I guess the question is how to define the motor parameters in your models.
Yes, motor parameters. Yes, they are normally given.
Inductors.
They are normally given by the manufacturers. So the manufacturers will give these parameters. But if they were not given, also you can use system identification toolbox, system ID, you can use to generate those parameters. But mostly the manufacturers will provide the parameters of those systems.
Okay. So, so as he mentioned, the inductors coil, so at least they will provide the number of the turn, right? And so they can reduce the LDLQ. So as Ahmad mentioned, nó thường nó sẽ được cung cấp bởi nhà sản xuất. Okay. Go ahead, Tú. Vì saturation nên sẽ phụ thuộc vào thải. Cho nên nó sẽ phải có một model theo LDLQ cái gì? Ý của em hỏi là như vậy đúng không Tú? Nên ý em là LDLQ nó sẽ thay đổi à? Okay, so it seems that his question is in the saturation, the inductor can be varied.
Yes.
So it depends on the load. So
Yes.
yeah. So the
Okay.
question,
This one
the
we.
equation. Yeah, I
Yes,
guess.
I understand what he meant.
You are
Normally we have.
Vietnamese now.
No.
Sorry,
What?
yeah. We don't need to understand, right? But we look at the parameter, we understand. Yeah, go ahead, please. Sorry.
Yes. So what happened is we have we call the parameter uncertainties, parametric uncertainties. This parametric uncertainties means the inductance, the capacitance, resistance, all these terms, they can change, maybe with change of loads or with change of temperature. So these parameters, we use parametric estimation. So we estimate those changes. We have a method to estimate those changes. We call, like, if you are talking of the L, the inductance we make is the L. This is the change, and we make estimation. So we have estimator, and this estimator is added to the system. We added it to the system, and it will estimate any changes of those parameters. I hope it is clear.
In summary, if I understand well, you will put this parameter is constant, and then
No. Okay, continue. Sorry.
And then you add the uncertainty for the variance of the LD and AQ as a function of frequency, temperature, and other parameter, but it's included in some kind of uncertainty parameter.
Yes. And we estimate it. We can estimate it. We can estimate these parameters. And when we make this estimation, we can see the changes, because ideally what he said is right. Those parameters will change and you might not know, and they can affect your control. But we can estimate those parameters. And when we estimate those changes, we can see how it changed, how this parameters changes. But initially we take it as constant. We said maybe it's 1, so but 1 plus something. This is the uncertainty terms. And when it changes, we can see those changes.
I see. Yeah. So, Tú is clear. Rõ chưa em nhỉ? Bạn ấy sẽ estimate cái sự thay đổi của nó theo tần số hoặc là theo nhiệt độ. Tuy nhiên thì nó sẽ là giống như nó là một cái hằng số, nó cộng với một cái delta L ấy, và cái delta L đấy nó sẽ là có thể estimate được trong cái quá trình mà bạn ấy sẽ mô phỏng hoặc modeling. Chị cũng không rõ lắm trong cái phần này, nhưng mà theo chị hiểu là như vậy. Satisfy chưa Tú nhỉ? Okay. In Vietnamese, he say thank you.
Okay.
It's clear to him.
Good. If he needs other discussion, he can talk to me. I have the material. I can even give him how we do this estimation. He can see how he can use it to estimate those parameters.
Very nice.
Uncertainties.
Yeah. Yes, that's great. Okay, so somehow we run out of time. Very interesting discussion. Thank you, Amma.